Hey, hope you're all having a good day. My name is Hector. We're going to go through question 65. A typical laboratory centrifuge rotates at 4,000 RPM. Test tubes have to be placed into a centrifuge very carefully because of the very large accelerations. So it's a two-part question. The first part reads, what is the acceleration at the end of the test tube? That is 10 centimeters from the axis of rotation. And B, for comparison, what is the magnitude of the acceleration a test tube would experience if dropped from a height of 1 meter and stopped in a 1 millisecond long encounter with a hard floor? Okay, so we're going to hop right in and draw ourselves a picture. So, getting out a circle here for part A, we can imagine some middle section right here, which is our axis of rotation, and our little point right here, which is our test tube, the distance between them, which is that 10 centimeters, and how quickly it's rotating. So that's going to be 4,000 RPM. Okay, so what we know about circular motion. So with circular motion, we know that we have some centripetal acceleration, which is noted like this, which keeps it from flying straight off of our circle. It keeps us going around. We then also know we have some tangential acceleration, so that's usually noted as such. And then we also have then this resulting acceleration vector, which tells us our acceleration, which is what the question asks for. It asks for this acceleration at the end of the test tube, which would be this resulting vector. So this question is made very, very simple once you make a really important realization. Because this is uniform, we're moving at a constant angular velocity, which is our omega and is our 4,000 RPM, our change in angle over change in time. We know that then, let's use a different color, our alpha, or our angular acceleration, is 0. And this helps us because our tangential acceleration is based off of that angular acceleration times our radius. So because this is 0, this whole thing just equals 0. Which means, as far as actually finding this acceleration, we no longer have this component to worry about. We no longer have to add this component and do the whole Pythagorean's theorem. We can actually just find our centripetal acceleration, and that's our only acceleration. So we're going to go ahead and do exactly that. Okay, so by angular acceleration and angular velocities and all this, a sub r, or the centripetal acceleration, is defined to be that a sub r equals, use this, omega squared times our radius, times how far away it's rotating from the center. And we can really just plug and chug, but there's a small caveat. We need to make sure that our omega, or our angular velocity, is in the correct units, which is radians a second. So doing a very, very quick conversion, one that I'm going to not really show because I'm kind of short on time, we get that 4,000 RPMs equals 18.9 radians a second. We can now simply just plug and chug away. So our centripetal acceleration comes out to be 17,547.7 meters a second squared. So a quick caveat, this radian just kind of fades away. If you remember from trigonometry, this happens all the time. I couldn't exactly tell you why, but it goes away and we get the meters over second squared, and this is our acceleration for part A. Okay, jumping right into part B, we will be looking at, to read the question again, the magnitude of the acceleration a test tube would experience if dropped from a height of 1 meter and stopped in a 1 millisecond long encounter with a hard floor. So let's go ahead and draw a picture, and there's basically two sections we want to think of for this part of the problem. We have, hang on, let me just label everything really quickly. We have our height, our 1 meter. We have our little test tube, and we know it's falling with that 9.8 meters a second squared, that gravity acceleration. We know that the ground is right here, and we want to think of this in two sections of time. So the first section of time is how long does it take it to hit the ground, right? So that's going to be, we don't know what that t is. And then how long does it take after it hits the ground for that 1 millisecond time, right? How quickly does it decelerate for it to get to that 0 position? So there's a few things we want to keep in mind here. We have this initial velocity up here, and we have, for that chunk of time, this blue chunk of time, we have this as a velocity final. This is also our initial velocity for this 1 millisecond chunk of time. And then we also have some velocity final for that. So I'm going to denote this just very quickly as v2 and v2. So velocity not 2 and velocity final 2. Okay, so first we want to do is figure out this time, how long does it take for it to actually hit the ground, so we can figure out how fast it's going when it starts to decelerate when it hits the ground. So we can kind of think of this with the known variables. What do we know? Well, we know a distance, we know an initial velocity, and we know an acceleration. So the best choice is a kinematic equation following this form right here, that x final equals x initial plus velocity initial times time plus 1/2 acceleration t squared. Using this equation, I'm going to go ahead and count this as 0 and this as the 1 meter mark. So we're going to get that the final position is that 1 meter. This is 0 plus our initial velocity, which we know to be 0. 0 times t plus 1/2. Our acceleration is again 9.8 meters a second squared times t squared. And we can just solve this out for t. Okay, now that we solved this out, which is this time right here, now we need to figure out how fast it's going when it hits the ground. So using a different equation and our known variables, we can figure out what that looks like. So I'm going to go ahead and go over here and just kind of solve that guy out. So we have that our velocity final, which I'm going to tub as 1 because it is this velocity final up here, is equal to our velocity initial 1 plus acceleration times t. Now we can really just plug in what we know. So we know that this is 0, this is 9.8, and we just solve for a time, and that time is 0.4516 seconds. That comes out to be 4.43 meters a second. So we get that this velocity right here, when it starts, this 1 millisecond is going exactly that fast. Now we can only focus on this second part of time, this 1 millisecond chunk of our scenario, and figure out, okay, well, if I know my initial is going 4.43 meters a second, how quickly to decelerate to get that 0. So setting the equation exactly for that, we're going to go over here and we're going to use the exact same equation. We now know basically the opposites of what we knew before. So we know that our velocity final 2 equals, I don't know why I used green there, but we used green, that 4.43 meters a second plus a times t. Now we're not looking at it for this 4.516 period of time, looking at it for this 1 millisecond of time. So a millisecond to a second is 0.001, and now we can just solve this out, knowing that this is 0, solve this out for a. Okay, So now we get this value out of our little calculation, and it's important to note it asks us for the magnitude in the actual question, this little bit right here, and the magnitude of any acceleration is just going to be the absolute value. So throwing some absolute values on these guys, we get at the absolute value of A. So the A we're looking for is 4,430 meters a second squared, which is huge. But comparing it to the acceleration we found before, it seems absolutely minuscule. And that's what we can do for question 65. Hope you all have a good day. Bye.